Okay, we should probably start. So welcome to the last one of the sessions on jet reconstruction in Atlas. Today we're going to talk about the point of systematic uncertainties, which are kind of complex in the context of jets. So when I put this together, I actually found that we don't really have much on the performance of jet reconstruction itself, in terms of a whole set of plots on resolution and linearity and uniformity of the signal. Those are all very old, and we don't seem to do them anymore, at least not for public consumption. So I'm going to spend a little more time on the systematic uncertainties actually than on the performance itself. So just a quick recap from last time. So we talked about the jet energy scale calibration in the Atlas, where prior to the calibration, the inputs signals are shifted to the frame of reference of the reconstructed vertex. This is, of course, the hard-scatter vertex. So this is only needed for the topo clusters, not for the p-flows. They're already assigned with this vertex. We apply a jet area-based pileup jet suppression, or pileup correction. Sorry, I should not say pileup jet suppression. This is not the main task of this one. It's applied independently for data in Monte Carlo. Depends on the median transverse momentum density of the event, which is measured independently in both cases. And then we need on top of that, we need a residual correction, which is determined from Monte Carlo and applied to the data as well, because of the poor reconstruction of the transverse momentum density beyond rapidities of 2.5. We then apply a simulation-based jet energy calibration, where we, from the in the simulation, we match a simulated detector jet with the truth jet, and by comparing the energies, we get the response. We can invert this and have a calibration. We refine this calibration by looking at other observables related to jets that can be reconstructed in our detectors, mostly track-based. Some are based on the energy sharing and the calorimeter. The idea of this process is that we introduce or correct some sensitivity of the response to jet fragmentation, meaning we apply a certain level of mitigation of the flavor content response variations and flavor response variations that we can expect. Then, after we have done all that, which is more or less all except for the jet area-based pileup correction, is all Monte Carlo based, we have to apply a final correction to bring the jet response, the calibrated jet response in the data to the one of Monte Carlo. So we look into in situ channels that are appropriate for this, typically consisting of providing a reference transverse momentum, which is well measured, and so like a photon or Z boson. If we balance this with the probe jets and by looking at the double ratio of the responses in data in Monte Carlo. Once we have that, we can combine the different various final states and cover the whole phase space with the jet calibration, where in the combination, the contribution from a given final state is weighted by the inverse of the error associated with this response contribution. Have the full phase space in transverse momentum and rapidity covered. So let's go to systematic uncertainties. This is actually a list of the most important publications. We don't have anything more recent, couldn't find anything more recent than is listed here. But I think most of this has them show you quite some detail, and they show you a little bit also the evolution of the story that we're looking at. So we said that the in situ jet calibration, this is a brief reminder, is not valid. Not all final states are appropriate for the whole phase space. So this table gives you an overview where the final state is most appropriate, and it also tells you at which level the probe jet is when you apply this final calibration from the in situ. The sharing, we looked at this very briefly yesterday, is shown in the next slide for two narrow jets, R0.4 jets on the right, and the upper plot is for the jets from P-flow, the other one is for jets from calorimeter signals alone. And you see that the sharing is strongly depending on which signal choice, the final state can play a role, and even analysis cuts or selection cuts can play a role. So these are not fundamental plots. In that respect, they change. Sometimes just because the pileup changed a little bit and the mitigation is not as efficient or comes up with a slightly different error. So the interesting part is that we basically have huge overlap between the different final states, and we can combine those to reduce our overall error. The combination is shown in and you see the response of data over the one of Monte Carlo, so the inverse calibration function is function of BT for some central jets, I think those are, and it shows the individual contributions from certain final states and the combination, which is the curve with the shaded area around it indicating the total uncertainties. So you see the uncertainties are very small, and of course, if you look at the data points from the individual channels, they look much bigger. So the combination itself is a complex process where we trace very carefully all sources of systematic errors, and some of them just simply cancel, so that the overall error gets smaller than the actually observed error in an individual channel. What is good news, came out last year, finally, is that for the large R jets, we actually get a very similar, very high quality calibration now going as well. This was not the case at first. We had problems to validate the calibration, but now we have a full in situ analysis for the large R channels, large R jets as well, including Z+ jet for large R jet and so forth. So we now have a very constrained system with a very precise calibration. So the idea of all this is to provide a universal jet calibration. So something that applies to all jets and data on Monte Carlo simulations. This is something that you technically really cannot achieve, but you can make it work for most of the jets. So the steps are, as we have seen, we calibrate jets to one nominal Monte Carlo, and then after the in situ corrections, we independently apply the calibrations such that we assume they're independent of the final state topology. And that selection that we did for the calibration, they're independent of the source of the jet, meaning which gluon, light, heavy quark it comes from, and they're independent of the modeling of the jet as a response simulation. So when you want to do something like this, what it really means is you have either you understand the different contributions and correct for them, or you have to have a systematic uncertainty that covers variations due to these points. And that's basically what we are trying to do. We have now reached a level where we really understand most of the things and very precisely and in large, really in the smallest details, but we still have residual effects that we have to capture in uncertainties and systematic uncertainties. I call them uncorrectable for now, which is probably can be wrong in a few years or months, depending on what progress tells us. Specifically, we are now we don't really have enough detector sensitivity to judge jet by jet the flavor of the object, and unfortunately, the response to the jet depends on the flavor of the jet, and there's two two elements that enter here. So when we do a calibration and have a jet sample, we not only do not really know the flavor response all that well, with the exception of B jets, where of course we have a full program to tag those and calibrate those. But we also don't know the composition of the sample. So we don't really know which flavors are in the sample. There's, of course, Monte Carlos giving us models, and we try to extract from these models, make assumptions for the data, but there's very little solid confirmation that these assumptions are really the right ones. If you look at some general pictures, you can see that they seem to be not too bad, but we really don't know. We have a residual issue with not knowing the composition of the sample in terms of the flavors that the partner flavors that generated the jets. There's always the issue of the event topology. If you have a low multiplicity jet event, jets are fairly isolated and things are easy. But if you get to dense jet environments, and this can already start like quarks, when you can have 6 jets or even more if you have radiation. So it gets pretty busy. So we have studied nearby effects, tried to understand those in Monte Carlos, and found they're relatively insignificant, at least in all the cases we studied. But there is still the fancier you get with your analysis, the more conditions you put on the event selection, you may enter corners of phase space and topologies that can be a problem for the jet calibration. So we are trying to catch as many as possible, focusing on standard model signatures with high multiplicity and low multiplicity jet final states, and see if we can see any response variations. One of the interesting features actually from high multiplicity final states is that we have a problem with the determination of our median transverse momentum density, because we have such a high occupancy in terms of jets in the central region of Atlas that the median is suddenly sensitive to the hard scatter, which kind of moves away from the original picture that the median is a good median of this transverse momentum density is a good representative of pileup. So we have an uncertainty was introduced to cover this part, and it has been observed in top decays indeed. So we have to have another look on this anyway to find out if we can do something else. There's also the general effect. If you apply calibration functions and numerical inversion, there's a chance that in the end, when you test when you try to validate the calibration functions, they may actually not close completely, or not with very high. You have certain closures at the % level or better. So it's typically not a big problem, but you have to keep that in mind, that the numerical inversion, for example, may not map correctly to the right response. And that is largely understood because of some non-Gaussian response functions involved in all this. There's another thing which we had to fight for a long time, which are large differences in modeling. For example, if you look at the dijet final states, we use a lot for calibration. We observe large variations in the eta intercalibration, especially, which were for the longest time the very dominating error, systematic uncertainty for the jet response in the forward region. Then the modeling of radiation, the extra jet and possible PT balance final states is, of course, not necessarily perfect. And so we also have issues from that kind of topology uncertainties that we have to take care of. Of course, we evaluate the PT balances as function of, for example, how much PT an extra jet has, or the angular relation between the reference object and the probe jet. So we can cover some of this and absorb it in uncertainties that in the end are very small. So when we do the combination, we use several measurements. They all look somewhat different, but they have common sources of uncertainties. So, for example, you can think about, photon jet and Z jet. In one case, we have a photon, which has, as an electromagnetic particle, certain set of uncertainties that it shares with electrons that are the basis of the Z reconstruction, for example, in the other case. So if we mix these final states, if we combine those to a common calibration, we should not double count uncertainties that are shared. Rather, we have to keep track of those. And we do this by basically creating a list of uncertainty components. These are later translated into what is often referred to as nuisances or nuisance parameters. Now, I forgot why I said uncertainty components are correlated. They can be correlated. They don't need to be correlated. Oh, now I know what I meant. That means they are correlated across the final states. They are not necessarily correlated between the components. I have to rephrase that before I post the slides. So we're trying to understand, where do these components come from? And clearly how the importance of any of those components may depend on the phase space, or there may be just a global nuisance, something that all final states have to suffer from. In any case, we need to make sure that when we build up the systematic uncertainties, we are not double counting these things. So we started with a long list, and we started to categorize them with respect to certain components. I will show you an example later. It's easier to see the contributions to individual measurements with a category. There's a modeling category. You can imagine there's a detector category and topology, or whatever the categories are. What is hard to do is the correlation between the components. It's often left to an education, to a guess. There's really not often we have experimental handles or measurement handles to determine those directly. At least in the beginning, we did, I don't know what they exactly do this year, but I think it's just, for the end of run 2, I think it's a similar thing. You can make two extreme assumptions. One is there's no correlation between the components, between the uncertainties of the given component, and there's 100% correlation. So these are the two things we test and see the effect on these assumptions. These components translate into a large number of nuisances. Nuisances directly are, I think, in our language, as far as I'm following this, is not the component itself. It's rather a projection of the component, including other components. It's a rather complex mathematical construct, but we have a list of nuisances that collect different contributions to systematic uncertainties, depending on what you need them for. There are a large number of those, and the software is available, but it's quite hard to handle those in analysis. They're typically 80 or so. I think we came up, the final number is 80 nuisances, or 80 that you can think of, that can lead to a very large effort in applying smearing to your results to see what happens to your final physics observable if any of these components change within their own resolution or their own error. So this is not often acceptable, and in some cases, in some analysis, it's not even needed. So the folks who are doing this came up with reduction schemes, where, for example, one of the simplest one was insignificant contributions are basically collected into one combined into one, which still, as a total contribution, may be small, but you lose some information about correlations when you do this, of course. So this we can actually look at. So here you see contributions to the systematic uncertainties for different final states. These are older plots, but those are the only ones I could find that are public, at least. You see that these from these different components we looked at are very different for the different finite states. Even if you look at like Z plus jet and photon plus jet, there's quite a different behavior. If we look, for example, the contribution of these electron energy scale uncertainties, it actually decreases with jet PT, while the photon energy scale increases. So this, despite the fact that the boson has electromagnetic showers, there's sufficiently different development in the uncertainties as function of the jet PT. This may purely be the case that harder photons are not as well measured as softer photons. There's also for the multijet, there are some topological parameters like the alpha and beta, those are angles, and then there's contributions from close by and so forth. And you see that most of these topological stuff tends to rise at higher momentum, but there's very little contribution from any of these particular ones below something like 100 GeV. Now you can ask yourself, this is just good old multijet. So why would I do multijets at 200 GeV when I still have coverage, or 100 GeV when I still have coverage from the direct balances or the photon and Z final states? Well, that's probably the reason that we have zero contributions, because they only start to get interesting for higher PT jets, and then we see the rise of the individual contributions. So this is all done automatically by the weights that we use, and then combining these different final state analysis to a common calibration. So this is folded in here. Oops. Okay, here's the list of contributions to systematic uncertainties. And you see it's quite exhaustive. You see there's a detector component, there's a mixed category, there's a mixed category, there's models, there's a statistical or method category. Method category means we introduce an uncertainty by going a certain way, by applying a certain approach, a certain algorithm. And so the numbers of categories is not terribly big, but you see some that are collected. And you see here, this is the three panels, so to say. The upper one is electron and muon related, so we're talking about Z plus jet, and there's a photon plus jet. And then there is the multi-jet balance. So once we consider all these components, we can actually measure the correlation between the calibration of jets at different PT. So this correlation is purely introduced by connections, by common systematics. So the old model that when I grew up, we measured PT of a jet in H1, and that had a calibration, and that was it. But the truth of the matter is that just to think about a calibration function and you fit a mathematical model to it, then you connect the low PT response with the high PT response, because the model may be constrained at both ends. And the calibration you finally get out of this comes from this constraint. So it's a little bit like this, just more complex. Here, the connections are the underlying uncertainties and the common sources for those. But you see these complex correlations. It is relatively clear that the way we are doing is with, for example, we are smoothing the calibration functions with the local spline, with a on a relatively short correlation distance, on a very short distance. That means the highest correlation is between jets with very similar PT. And then it clearly drops off when you get into off diagonal regions where we have now more subtle effects that introduce again a correlation at a much weaker scale. So this is another one of these correlation matrices. This is an older one. Oh, no, sorry, this is a newer one. This was the old one. This is a newer one. I just show it because for this one we can look at some of these things that happen when you do a reduction. So on the left, we see again the correlation matrix in PT. On the right, we see the correlation matrix actually in jet direction in a given PT bin. So we go in this, in the digest system, we go into this bin where both jets have 60 GeV PT. And then we measure the correlation eta. And you see that it's very strong. And it kind of has to intercalibration. So we are correlating the PT response in the central region with the PT response in the forward region, and that is what you see in these plots. So that is not a big surprise, and that's also why you don't see many of these eta plots, because they're really not these directional plots, because they're really not very useful to look at. So, as I said, the large number of uncertainties and correlations may be hard to manage in an analysis context. So there's a lot of work went into trying to reduce the set of nuisance parameters while preserving the most relevant correlations. So there was a reduced set of nuisance parameters available where the out of the 80 total, 67 are actually related to the in situ nuisance parameters. Now, if you decompose these correlations into principal components, you find 19 that are really relevant. So those are the ones. 19 in total now, because they're combining 62 into 1. So the correlations are so small that we can safely combine them to 1. And now you can ask yourself, well, first of all, there's a strong reduction, but let's first ask ourselves what happens when you do this. So when you do this, you can measure the differences between the two correlation matrices you get. The one that is the full detail and the one that we don't show here, but that has only 19 nuisances to couple PT bins, nuisance parameters, I should say. So the difference here is very small. The average value is actually 0, and the maximum observed distance is 1% in the correlations. So this is very small. But if you go to a stronger reduced set, if you combine more nuisance parameters into a big chunk, you see the effect can be larger on the correlation itself. So here the mean value is 13% across the whole PT plane, and the maximum observed is a change of 39%. So we depending on this may still be good for a given analysis. So the trick is to find the right reduction or use the full set of parameters for your given analysis. So there's a little bit of exploration that people have to do, just looking at what are the contributions to the analysis, what is the most important, what are the most important contributions, most important sources of uncertainties, and then choose the right nuisance parameter accordingly. So once we have all this, we can now collect the systematic errors, taking all these correlations into account. And we get the results shown on this slide now. And you see in the right column, you see the P-flow jets and the calorimeter jets. This is a slightly older plot on the P-flow jets. There was significant improvement at low PT, so they are at least as good as the calorimeter jets now. Again, these are all public plots, so I didn't update them with maybe more modern versions of not yet public results. But you see that we have a large area, especially, let's say, a few hundred GeV to nearly 2 TeV, where we have an uncertainty of 1% or less. So this is for a hadronic final state object like a jet, this is a fantastic result. This was unthinkable when I did jet physics a long time ago with a different experiment. We were happy if we had a 5% uncertainty on our jet energy scale. The fantastic thing for Atlas is that also on the left plot you see the same thing now for the large radius jets, including the local hadronic calibration. So here it's clearly very nice to see that we are down at the level of 1% as well. You also see where the work still is. There are a few ideas. We can see what we can do at the low PT end, but the real issue seems to be the high PT end. And the reason for that is very simple. We are just losing reference objects in situ. So we don't really have a good final state anymore that we can use for validation of the calibration beyond about 2 TeV or so. Also, that includes the multi-jet final state. The multi-jet final state, multi-jet balance is a bootstrap problem. You start with balancing an unknown large PT jet against a system of well-calibrated lower PT jets. But of course, all the systematics you got from the low PT jets are in this balance. They're not going away. So it's very hard to do this calibration for very high energetic or very high momentum jets. There are approaches using decomposition of the jets. We look at the particle content and try to understand the response inside the jet using the well-known uncertainties on the responses to individual particles. This is certainly a nice guidance, but these jets are not only high energetic, they're often very focused. So we don't really see individual particle responses in the calorimeter, for example. We see a lot of merged responses. So it's a non-trivial exercise that is still pursued. So let's go for the last few minutes to some performance issues. The whole systematic uncertainty is a science by itself, right? You can probably need 3 weeks to get through the topic and the math of all of this. But I think the important thing is this is a way to control the systematics by eliminating double counting, by including the correct components, contributions, weighted by the contribution of the particular measurement that contributes to the calibration. So this is now a well-exercised framework. We do it every year again, and we will continue doing it for run 3 and probably for run 4. So we have talked about pileup suppression in jets, the step before calibration, which is basically aiming at the removal of diffuse particle emissions into jets. We saw that the jet area-based pileup subtraction can do this with a slight modification for jets outside of rapidities of 2.5. What I want to talk about now is actually the suppression of pileup jets. With the jet area-based, we can shift some jets below the threshold we have for reconstructing jets, typically 20 GeV, by subtracting the median density times the jet area. But it doesn't really mean that we have removed the pileup jet. We may have also removed a soft jet belonging to the hard scatter. The reason for that is the median transverse momentum density is an event quantity. It's not sensitive to local things that happen. So in addition to all of this, we have pileup jet tagging. So this is the idea now to actually look at each jet and try to figure out how much of the jet comes from pileup vertices or is it too much? Is it really a pile-up jet? Or is it a hard scatter jet still? Those are estimators that we use, that we get from the tracking, where we have very precise vertex determination. So the first thing we do is, or the one thing we do is the jet vertex tagger. So the jet vertex tagger has two basic inputs. It started out with something we did a long time ago, which is this jet vertex fraction, which was good until 2011, I think, which basically sums up the scalar, produces a scalar sum of the transverse momenta of tracks coming from the hard scatter vertex and pointing to the jet over the scalar sum of all PT of all tracks pointing to the jet. So if this is a number is large, then clearly the jet comes from the high scatter, very likely comes from the hard scatter vertex. Now it turns out this will rise if the pileup goes up. So this ratio will go down but at higher pileup automatically. So in other words, it's very hard to fix a working point, saying you would have to adjust the cuts with the pileup, and that brings all kinds of additional uncertainties and probably needs to recalibrate quite often. So we really didn't want to do this. Instead, we modified this a little bit, had a corrected version of it, which is basically the same ratio, except the pileup contribution is moderated by some constant times the number of tracks from the pileup vertices. So this takes advantage of the fact that the total PT coming from these vertices is proportional to the number of tracks or the other way around. So it kind of moderates down the PT contribution from the pileup to a fixed scale. And if you do that, then you can have a fixed working point, as you can see in the little plot down there on the right, bottom right, where the efficiency to keep your signal jet is literally flat as function of the number of primary vertices in the event, which is a good measure for in-time pileup. What you see if you apply the old method, you see this efficiency dropping, and so it's completely inadequate for analysis to have to deal with this kind of efficiencies. In addition to this one variable, we also have a second one, which is the track PT response to a jet, where we only consider the tracks coming from the hard scatter vertex and divided the scalar sum of their PT, which is divided by the PT of the calibrated jet. So the idea is pretty similar, but if the track vertex association is efficient and the vertex reconstruction is efficient, then this number doesn't depend on pileup at all if you had applied a mitigation of the pileup to the jet as well. So, I mean, there's this likely small dependence, but when you look at it carefully, you can see that as the number of the vertices, this is also flat for a given target efficiency. This was 90% in this plot on the left, and you also see that the spectra of this quantity is very different for hard scatter jets and pileup jets as expected. If you put all this together into a ROC curve where you measure the fake rate versus the efficiency, you clearly see that the JVT green dots perform very well. So JVT actually combines these two measures into forms a score out of these two variables. And you see that the RPT alone, the blue, is actually doing pretty well by itself, but there's clear improvement to include the modified corrected JVF, and you find the green curve, which is the final JVT. So JVT is a standard tool. It's used now. Everybody jets in the state. Fortunately, it's limited to the acceptance of the tracking detector. We only apply to jets within rapidities of 2.4. And it's also limited in terms of if the jet PT is large enough, then the likelihood for it being a pileup jet is getting very, very small. So we only do it to jets up to 60 or maybe now 100 GeV. So the next and last step that I wanted to show you is actually the relative jet energy resolution, even though it may not be as important as it used to be in the old days. So one of the main contributors, which we just have, is the noise from pileup. It will fluctuate the jet signal, the detector response, as we have seen due to the effects from the shaping function and the changing proton beam densities and so forth. And for example, also, as you know, in LHC, we have bunch trains, so there's gaps between the trains when there's no energy in the detector, contribute to a noise. We can measure this noise by the data Monte Carlo independently, and we do this by the random cone approach, meaning we put two random cones in the event. In data, we can take, we just take zero bias data, which basically has no jets to begin with. So we can put them anywhere. If you have jets in the final state, you may want to stay away from those with your random cones. And then you calculate the difference in PT in these two cones, which are empty. So this is just a difference generated by noise. And you see the plot on the left. It should really be centered at zero and has a certain width depending on the resolution, on the noise itself. So if you look at this evolution of the noise as function of the pileup, I don't know why I lost the axis label here, but I will put it back. You see that for the calorimeter jets, the green points, the noise rises with the activity from the pileup. It also does for the particle flow objects, because the jets, the cone includes not only those objects, but also calorimeter, neutral and charged particle flow objects. So there's a calorimeter component still there. But it's a little moderated in terms of slope, and it's certainly at a lower level. So the noise values are just lower, which is always nice. You also see in the same plot that Monte Carlo predicts actually the open markers are all corresponding Monte Carlos, predict actually a higher fluctuation from pileup than the data observes. So this is one of the another pointer to the inability of in the Monte Carlos to generate pileup or to model pileup adequately. So we have other terms contributing to the resolution, as you probably know. We have a sampling term, or it rather should be called stochastic term, would be more appropriate, and a constant term contribution. The constant term is the high energy limit of the resolution. It's often governed by the quality of your calibration. For example, how well you could actually mitigate non-compensation. The stochastic fluctuations come from the fact that you have a sampling calorimeter, and they are largely correlated with noise effects for low signals, especially now pileup. So the calorimeter has a significant noise contribution at low energies in the presence of pileup that contribute to the stochastic term as well. So you select you do topology cuts based on the third jet and all these other things, and then you balance the PT of the two jets. You calculate the asymmetry, which is the difference of the PT over the average PT, and from the distribution of this, you can extract the resolution, the jet energy or jet PT resolution of the jets. We do this for calorimeters on the left and for topological, for particle flow jets on the right. I put a few lines on this plot just to tell you where the 15%, 10%, and 5% of resolution lines are. And I try to, by eye, translate them into PT thresholds. You see that above something like 80, 90 GeV, both behave very similarly. Maybe the P-flow jets get a slightly worse resolution at higher momenta, higher transverse momenta, but below that, in the low energy regime, clearly the P-flow has an advantage of having less fluctuations, and thus a better resolution. So, yeah. So we have an improvement on the low PT resolution. Remember, that's not the only improvement from using particle flow. There's also a directional resolution improvement, which is probably even better. The fact that the better resolution, while the pileup noise was a little higher, tells you these plots actually, what is shown is actually unfolding the pileup noise and the fluctuations at particle level, which is a procedure I personally don't quite agree with, especially the last one, because the fluctuations at particle jet level only can come from Monte Carlo. So you have a Monte Carlo contribution to your experimental detector resolution, but Atlas has agreed to do it this way, so we're doing it this way. So you don't see, if you want the effective resolution with respect to a partonic energy flow, you see what the detector does out of a bundle of particles, which is it's an okay measure. It's nothing is wrong with it. So having done this, you do systematic errors based on, again, Monte Carlo and data comparisons, and you get several contributions to the error. You find that in case of the p-flow, the errors are considerably less at lower PT than once the systematic uncertainties are less. I think I'm not allowed to say error, actually. But okay, systematic uncertainties are less for the particle flow as well. So there's a good reason why we moved to particle flow. It will be our standard jet signal for run 3. We still will reconstruct the calorimeter jets as well for double checking. So I think I'm done for today. So I think I could at least send a message that we have a very precise jet energy measurement. We have a acceptable resolution. There are not many analyses I'm aware of that are limited by our jet energy resolution. And we have tools to tag jets with respect to their source with a possible origin from pileup. So that is where I wanted to be after this. We started on a slightly different issue, and we're looking basically only at large R jets from now on. So, are there any questions? Okay, Kuan Yu.
Hi, thank you for your lecture. Can I add something maybe you didn't cover, or I think you might have in the slides that miss it? So, when I study the uncertainty of jet energy resolution from the TV key, and then there's this procedure of not only smearing Monte Carlo, but also smear data. And the justification is that there is anti-correlation, and my understanding is because of the fact that you use a dijet asymmetry to do it, so there's anti-correlations. But could you comment on what that actually means, the anti-correlation?
Okay, I'm not quite sure I know what you're talking about. I haven't looked into this. I haven't looked into resolution determination for a long time. Mm-hmm. So what you do is you when you have a resolution, what are you smearing? The resolution function itself, or?
Yeah, in my, I try to understand it by reading the Athena code. So it looks like they, the fact that the JER is different between MC and data is by you, let's say if your resolution in MC is 15% and in data is 20, then you calculate, you know, the difference in quadrature between the 20 and 15. So I forgot how that might be, maybe like 5%, 8%, and you smear your jet energy for MC by that 8%, sorry. But then they also say that you have to smear data in the way that's in the opposite direction, but by what amount I didn't quite understand. And then you have to do both at the same time. So you have to smear MC and then data, but then in some opposite direction by some different amount.
Yeah.
Yeah.
Is this the uncertainty provider for the jet energy resolution? The code you looked at?
Yeah.
Okay. I mean, I don't really know the answer, but I can probably find it out and maybe post something on the agenda. But one of the things is there's a common element, which, you know, what they do is they take the measured resolution from the data and subtract in quadrature the expected resolution introduced by the particle jet itself. So you know that the fragmentation is a stochastic process. You have variations, and this leads to fluctuation in the response to even the cleanest jets you can define. So this part is subtracted from the data as well, which makes somehow Monte Carlo enter the determination of the experimental resolution. So the curves you see are actually detector level resolutions, and everything else is supposed to be subtracted. I don't see the anti-correlation. I have to. No, I don't see it without at least looking at the code right now, which I can't. So I only have a very small screen here. So I will see if I find out something and maybe comment on this the next time. I mean, give me a few days. I'm not very familiar with the uncertainty provider for the jet energy resolution. So sorry for that.
Thank you.
Okay, do we have any other questions? Well, if not, then this was it for this week, and we're gonna start with the substructure stuff next week, which will be the last 3 of those. I will post the slides as soon as possible, and I will try to find the answer to the last question about the anti-correlations. Well, thank you for listening, and talk to you next week.